Good evening, Jyotirmay. How are you?
Good evening, Sreji. I'm fine. How are you?
Good as well. Great. Any questions? Anything?
Well, actually, I was trying to solve a question. Maybe I can uh, give it on chat.
Go ahead. Go ahead.
Sure, because the answers are not matching. So I'll just a second. So yes. So
Yeah, go ahead.
yes. So while solving this question, we can see that we have to find out three things. Basically, the change in internal energy and change in enthalpy, and finally the total work done. So as far as the internal energy is concerned, that we can use find out using the value of the m is given, Cu is known, and delta is known. So this value comes out 18.25. But while trying to calculate the total work, because it is a closed system, and then applying the first law of thermodynamics, where you can say Q is equal to U plus W. So then since Q is equal to 0, because it is shown to be an adiabatic process at constant pressure, so then W should be equal to minus U. However, this value is not matching total work done.
W should be minus what? Minus C, is it?
Since Q is equal to U plus W, so we can say W is means W is equal to minus U.
Minus U. Okay. Minus delta U.
Minus delta U.
More correct. Just give me a second.
However, none of the
System contains. Okay. System contains a paddle wheel arrangement as shown in the figure. Uh, Jyotirmay, see the
yes.
system is a paddle wheel arrangement. So are you also considering I don't know, let me read this entire thing. The system undergoes an adiabatic process at constant pressure. Okay. The system has 0.2 kgs of air at 140 kilopascal. Upon receiving a work of 0.019 kilojoules, okay, the temperature rises from 5 degrees Celsius to 127 degrees Celsius. Okay, upon receiving so much amount of work, uh, the temperature should rise. The paddle wheel arrangement is shown.
Yes. So if we start, then we can initially start by solving for internal energy.
Suggesting, and this is an adiabatic process, contains air, so air can be considered as an ideal gas. Then you're saying, so basically delta U is PV into delta T, which is like 122 kelvins into 748 into 0.2 kgs, which is how much?
Which is 18.25. So this is matching. So 18.25, it comes
18.25
around
matches. Okay.
matches. Yes, so matching. This first part is solved. Now, second part is if I go on top, that is calculate the work done, then I know that Q is equal to U plus W. And it is mentioned over here that the system undergoes an adiabatic process at constant pressure. So if Q is equal to W, then I should be able to equate W equals minus U. However, the options are not matching. So if what I'm missing, I am
So,
unable to
but
answer.
see, the question also says upon receiving a work of 0.019 kilojoules.
Hmm.
See, you're missing two things. Uh, Calculate the total work. Uh, okay. So, me essentially what we have is, as you're mentioning, delta U. Delta U is Q plus W. And now let's break the W to be say W external plus W boundary, right?
W boundary. Okay.
Boundary work. What PDV? Let me write PDV, right? So now we know that delta U was how much? You said delta U was 18.18
18.25 kilojoule.
5 kilojoules, right? Q is 0 joules. And we are also told that work external. I'm just considering, see, there are two kinds of work going on in here. One will be the boundary work, and the other
Hmm.
is the work by the shaft work or
Yes.
paddle work. So then this external one becomes 0.019 kilojoules, right?
Yes.
Right. So now what
0.019
is
kilojoule.
work done by PdV? Is roughly 18 only, right? This is 18.23 kilojoules,
Yes. Maybe. Okay. It was 18.25 minus.
right? On receiving a work of this much kilojoules, the temperature changes. Estimate the change in enthalpy of the system for the system. CVCP. Okay. What about the answer to 9?
9 is also not matching because in case of the change in enthalpy, what I'm doing is I am applying the formula of we can say that H is del H is equal to Cp del T, or means all the overall energy will be and del H Cp del T, and over here we know the values of Cp by Cv ratio for air. So from there we have to derive Cp from Cv, and then we can get the value of H. I means I am
This
following
is
that
this is
approach.
from NPTEL
Yes, yes.
NPTEL.
Yes.
Okay.
So basically, I'm trying to solve, but these two answer is not matching. So means I was just trying to figure out then maybe some other formula we use or what I'm missing.
No, I don't think so. Formulas are okay. The values are also very different. Like question
Yes,
number
yes.
8 and question number 9, they should match. Like as you mentioned, no gamma,
Hmm.
right?
Yes,
And
yes.
then
For
this
yes,
upon receiving a work of 0.019 kilojoules, that is also a little, maybe there is a issue. Did you try sending them a mail last time?
No, I didn't, but what I have done is that means there is a feedback option. So what I will do is that I will try 2, 3 options and then give in the feedback in the because in the course as you progress there is an
Feedback
option
won't
below
help
that
you.
section.
Feedback
Okay.
won't help you. You try to reach them out.
Okay, then I will surely mail them only.
Feedback won't help because feedback is um, a routine process they follow. So that will not help. Anyways, hmm,
Okay.
let me try one thing. Just for sanity checks, just to make sure that we are not making some silly mistakes. Let me feed this to ChatGPT once.
Wow, yes.
At least we will know if we are making some stupid mistake or not.
Yes, yes, yes.
I don't think so though. Let's see. Units issue is there, I feel. Even then when you say total work, should be boundary work, I feel.
Yeah, but even then there is a big difference. Units 1 maybe, as you said.
Yeah, I understand. I think it should have been something in like they have changed the units. This should have been in joules or something, I feel. See with 18.25 into 1.4, right? Is how much? It will be roughly 18 plus 10, 27. Something so 18.25, right? Yeah, 25 point something. This should have been option A could have been an option,
Yes.
right? Or 255. Like if it were in joules, not in kilojoules. Even then, that this is a unit issue. Even then, it will not be working. It should be 25.1 only kilojoules. Won't work. Let's see. Let's see what it says.
Okay.
Don't think this formula does. I don't think this is the right formula though. I don't think this is the correct formula. Let me think. Total work input. Does it say total work input?
Total work input, total work input. Uh,
Total work only, right?
Calculate the total work in kilojoule that is required. Like that it is said.
To the required amount of work.
So yes, we are getting means yes, this is this. Then suddenly in the scaled gas per option, the correct multiple answer corresponds to means 54. That I know.
Total work required is 254.
Means
How
how
come?
that is. So as per formula, it's in W total is del U plus W boundary. Still, it is not like
Two from the, what do you say, NPTL side. Because they always rerun this course and then they won't, these are non-technical people making the assignments. They don't make sure that the questions and the options are, this thing is robust. So they'll update the numbers, but They will not make sure that the solution is correct or not.
Okay.
Yeah, that happens. That is why I'm saying write to them.
Mhm. Okay,
Right?
this one you
This is something wrong only. That is the
maybe
issue.
0.2 kg
Hmm.
or 0.2. Okay.
Even then, I don't understand why this formula, where does this formula come from?
Hmm.
What do you think about
Yes.
this? What do you think about
Yeah.
this formula?
W total. No, no, no. Means W total is W plus W boundary. I mean, no, no. I
How does
don't
this,
know how. No, no, no. I don't
this,
know.
right?
Yes, yes.
Anything else do you have? I don't know. This is unresolvable, I feel.
No, no. I was trying to solve. So these things I was having thing
Yeah,
because as per the formula given, it
whatever
is
you
not
are doing
matching.
seems to be correct.
Okay. So I will
Yeah, I
really have
think
to write
whatever
them
you
then.
are doing is correct.
Okay. Thank you.
Yeah.
Because I was also means sometime, so it was not matching. I thought. Okay.
Okay. If you have anything else, we can discuss that as well. Otherwise, I'll just discuss whatever I have.
Yes, yes. I think nothing else. So maybe you can discuss, and also I will be good for me for revision. It will be.
So, couple of objective questions first. Internal energy is a function of only temperature. Is that true or false?
Internal energy. Uh, yeah, I think the option is true. Internal energy, function of temperature.
So it's this is false.
False. Okay. Can it's not only temperature.
So when is it? Okay, tell me this. Can I write this? U equals to C. Can I write this?
To U is equal to CVDT. Okay.
No, I'm asking. Can we write
Okay.
this?
Du is equal to yes, we can write this also.
You cannot. Okay, this is not correct.
Okay.
You write wrong. Sorry. Okay, then can I write this?
U and DH.
This should be a little straightforward, but primarily what I'm trying to ask is how do you define? Let me ask this separately. How is CV defined? Can you give me the definition of CV?
CV is like the specific heat capacity at constant volume.
Okay,
This is
so specific capacity at constant volume
of gas at constant volume.
of gas of what
Of means the fluid that we are considering.
of the okay of the system. Let's say system, right?
Of the system. Yes.
What is specific heat?
Specific heat is the for the unit temperature rise, the amount of heat energy that is involved.
Amount of energy.
Involved.
Should I say energy? Which energy then? You mean to say internal energy?
Yes, internal energy. Uh,
So let me say specific
uh,
uh, heat capacity
heat capacity.
within Let me type your name as Jyotirmay says
No, it's okay. It's okay. No problem.
specific heat capacity can be defined as amount of internal energy required or using involved to change unit temperature. Is that what you that is what you were saying, right?
For a unit mass,
Per
and
unit
temperature.
mass. Yes, yes, yes. So for specific unit per unit mass, correct.
Huh.
Is this fine?
It can be defined as amount of internal G amount of heat energy. Yeah, it's amount of heat energy or internal energy.
Amount of heat energy, not internal energy.
It should be heat energy.
Now, what is heat energy?
It is the energy transition across the boundary. Internal energy is something which is stored in the system, but the heat energy is always the boundary phenomena.
You're saying Q.
Yes.
So just to be a little precise, when you say heat, you say either heat, you don't say energy along with it, or if you mean energy, then you don't say heat. Heat is a form of energy loosely, but as you said, right, there is energy is a state. Generally, energy whenever we use energy is a state property, right? Total energy or internal energy, right? Kinetic energy. All of
Okay.
these are state properties, but heat, as you said, is a path function, is at the boundaries. So we don't associate heat. Essentially, what you're saying is cross constant volume process Q dq or del q. Okay, could I say dq? I cannot say dq, right? I should say del q by dt is cv. Is this okay? And I will use three straight this symbol for definition. Or let me be more precise. I'll use the correct symbol. More precise symbol. Operators. They will. The correct symbol should be somewhere here only. Let me see. Yes. This is also correct, but I want to use. So what do I mean? What basically am I looking at? Uh, the symbol I'm looking at is this one. This one. Delta equal. Let me try if I. So basically, I'm defining it to be this. Okay.
Okay.
It's defined to be this. Essentially, I want to use this symbol where you have an arrow over these two lines. Okay. So
Okay. That means
this is
it is
what you mean, right?
exactly equal, but some approximately equal, something like that.
No. That is different. See, uh, how do I differentiate this? What definition is universally accepted? That this is the definition of. See, mm, see, you're defining CV in terms of this, right? This is what you meant. And not even this, you also wrote M. So you are also writing as it as 1 by M, right? where m is the mass. So one thing is this. What do I mean is, first of all, let me see. This is also a symbol, right? Let's use definition. This is okay. We can triangle. Okay. We'll use this symbol. No, this is not the right one. Oh no. Waste time on this, but anyways, it should be somewhere here. This is what I mean. First of all, I can copy this, but I can use it. This is what I mean, okay? This is a symbol that you will see. Let me also think of something where we actually use this symbol. So for example, in a triangle, we know. So if I were to write something like sine of alpha is equals to a by c or something. You call it some a by c, right? A by b, where b a by c, right? Or here you actually define sine theta as this. This is how we have defined sine alpha, right? Sine operator, right? You understand
Okay.
my point? So
Okay.
this is
Sine
what I'm trying
operator.
to sine
Okay.
operator. Whatever, anything that we define, we use this symbol. This is different from simply saying equal to. Okay, because equal to is not just to differentiate that this equation holds by construction. We are constructing sine to be equal to this. You understand?
Okay.
See, sine alpha equals to this is also true, right? This is also true. And this is an identity. We know that sine square alpha plus cos square alpha is 1, right?
Okay. Yes.
But this is an identity. This is not something that this is not how we define sine alpha. So just to differentiate the defining equation, I'm using this symbol, and I would rather not use this symbol, but use this one. This is also the same symbol, okay? This is also the same symbol. This is also used in mathematics to signify that this is a defining equation, okay? One thing. Another thing is what you said about approximating and all those things. So let me show you that that symbol is approximate symbol, okay? You have this, or you can
Okay.
have this, right? This is
Okay.
like A is roughly equal to B and something on that side. There is another symbol. This is also loosely same thing, approximately, but this is not approximately equal to. This is called as something is on the order of something else. So 10. So what I can say is 10 is uh, on the order of 20, but this is all not relevant to whatever we are discussing. but just for the sake of completeness, I will just close this loose end. But when I say 10 is not the order of 10,000, okay? So in this case, we can't use the symbol, we use this thing. Ever. So that I don't see it here. Basically, what I mean is this symbol with a cross now. So we'll insert a cross here. Okay. Because it is not on the order of, so 10 and 10,000 are very different. Okay, so they're not approximately equal. Approximately would be 10 and 10.05. Yeah, let me write that also. So when we use approximately is 10 is equals to approximately equal to 10.05, right? But 10 is in the order of 20, right? Or I can say, let me give you more feel for it. 0.8 is approximate is on the scale of 0.9, right?
Okay.
Right. Okay. Anyways, going back, so just you want to say that we are defining CV by this, and this 1 by m can be absorbed in Q to write heat transfer per unit mass. So just the small q instead of a capital Q. Okay. This is how you define things.
Okay.
Okay. So now if I invoke for the case of constant volume process, right? If I invoke energy conservation, then what I write is right. This is okay.
Yes, this is okay.
And for a constant volume process, we can actually uh, suppose this is a simply compressible system. Okay. There is no other work. So can I write del W as PdV?
Yes, but isn't it supposed to be Q is equal to del Q is equal to del U plus del W? It is.
So those signs, Acha, you are basically concerned with the signs, that
Yes,
minus
yes,
or plus W. So that will
yes.
change essentially what.
Okay, as
Okay.
per requirement. Okay.
So that is how. So basically, when I write this, I'll tell you how I remember it. Essentially, how I'll just tell you how I remember it. Why, like, what is my understanding when I write this? I'm essentially saying that there are only two ways of enhancing or increasing the energy of the system. Either you add heat into it. So
Okay.
basically Q here is heat input to the system, and W is again work into the system. It's not work done by the system. Okay. So this plus and minus, this is how I generally write conservation of energy. Okay. So anyways, so this del W will become PdV. PdV, actually PdV. V specific volume, it will be specific volume. Okay. And as you mentioned that in case dV is 0, it's a constant volume process. So we can actually substitute du instead of d del q, and we can write this, isn't it? But this is not the mathematically precise statement. You have to write this. You have to write this. Okay. This is important. Do you understand what this symbol is?
Means I don't remember the name, but yeah, it is how we write.
We write that under the assumption, under the constraint that specific volume is constant, only then CV is equals to du by dt. So this is wrong. Okay.
Okay.
This is incorrect. What is correct is, the correct statement is this, as we had already written this thing down. And I just wanted to say that this is how I define CV. Okay. Just okay. Now, okay. So we'll stop this. So I'll also remove your name now, because this has now become more general, right? Right. Now this is correct. Whatever we have said, amount of heat, right? Or we can also say heat transfer. Generally, we'll say also, as you mentioned, no, because this is a boundary thing, there will be a transfer happening between the boundary and the surrounding. So we generally say amount of heat transfer, or you can say amount of heat is also fine. So that is not what do you say necessary. But anyway, that is a colloquial thing. That is something some writer would prefer. Okay, that is up to your choice, right? Anyways, so now you tell me when you mentioned, when you thought that internal energy is a function of uh, only temperature. Why did you say so? I also mentioned, so just to just to keep the discussion flowing, uh, I have written du equals to cv dt under certain. So I've written not always, right?
Yes.
I've written not always, right? So my question is when? That is my question. So rather than simply just telling you that this internal energy is not a function of temperature in general, let me tell you when it's the only a function of temperature. Can you tell me? I think this is something that you have already done. So can you tell me this? The idea is, I'll tell you. The idea is, oh, were you trying to answer?
No, please go ahead. I'm following.
Okay. So the idea is this happens only for ideal gases. Okay. Now, what will this mean? What will this mean? So, first of all, let's first think when, like, what does this mathematically imply? Okay. What does this, like, generally we know CV is this, okay. But now I am writing. So, essentially, what am I writing? For ideal gas, this is what I am writing, right? For ideal gas, I can remove this constant, the constraint of constant volume, right? I can just simply remove this. This is what I'm saying, isn't it? Or now I actually
Yes.
will remove this
Yes.
also. I will see. I'm also doing some another thing. I'm also removing that 3 bar equality. Now I'm saying CV equals to du by dt. This is not a defining equation. CV is equal to du by dt for ideal gas. That is what I'm saying. Now, why does this follow? For an ideal gas, when the specific volume is constant, why CV is only function of temperature. So there is actually an identity that we need to remember or know to actually know this. So what do I mean is for ideal gas, this follows. Okay, this follows. CV is a so in generally, I'll tell you generally. Okay, one more thing. So before so this is also true. Okay, let me move to another page. Continue my discussion. Acha, let's forget for some time that we are discussing anything on ideal gas. Okay. Can you see why this follows? So what do I mean is from this equation, so what do I mean is from so this can you understand this statement? Can we talk about
So
this?
this means the CV is basically the function of temperature and the specific volume that we can see.
But the question is, how did I imply that? From saying that it is a function of temperature, like this is a gradient at constant correct gradient, right? In internal energy. How does it become a function of temperature and specific volume? So before answering that, we'll discuss this part also now for some time. But tell me one thing: for any guess, for any system, can I write this in general? I'm not saying that always, but in general. Tell me, Jyotirmay. Maybe you're there, so we
Yes,
can discuss. So that's
yes.
why I want to just discuss this with you. Can
In
you tell
ge-
me why would I write this? Or can we write this or not?
means yes, we can write this, but it is mostly applicable for ideal gas.
Is it? Is it?
Or means actually in general also we can write.
Why? Why?
Uh,
Where is this coming from? Is essentially that is what I'm trying to force you to notice. See, do you remember our earlier discussion of state function and state point functions, right? What
yes,
did we
actually,
do? We
briefly
drew
recall.
a state space diagram. What did we do? We said that there is this. We said that there is some state of the system, and then it will traverse and do its own like things, and it will move to a different state, right? That is what we did, right? And what we essentially were doing was we drew our two-dimensional state space, right? There was the state, what do you say? The state space was a two-dimensional thing, isn't it?
Yes.
We had two independent. You remember Gibbs phase rule, right? It says
Mhm.
that if for a pure component, we saw this also, right? For a pure species, you will have 2 degrees of freedom.
Yes.
Do you remember that?
Yes, yes, we had
Essentially,
discussed.
right? Essentially, that is what I'm writing. I'm not writing anything else. What I'm saying is, I'll just quickly write this as for for a pure substance, single component system, Gibbs phase rule follow that there are 2 degrees of freedom. Essentially, that means that any state function can be written as a function over two independent state variables. Do you recall this part? Like, I think you know, right? This part,
Yes,
you know,
yes,
right?
yes,
That
yes.
is what we are doing. I could have essentially written the same thing as this. So in this case, I cannot write anything much, but for internal energy, talk about total energy, not even internal energy. Uh, Let me write for internal energy only, not total energy. Uh, for internal energy, you could have written this or even this, right?
Yes. As a function.
Or it's your choice, right? T comma T. Right?
Right.
So essentially what I'm saying that any state function can be any state. So important thing is any state function. Now let's go back to our discussion here. Note how CV is a function of u. It's a slope, right? It's a slope of how u varies with temperature along constant volumes or constant densities. What do you think? CV is a state function or not? CV not be a state function, or why will? Let me ask this assertion. Is also a state function. Do you see why? Can you try to answer this question?
Well, it is a state function because it is dependent on these variables. It's a,
No, but say if this was not given to you, say I remove this part. Now you tell me, can you say anything why CV will be a state function? You could, right? You could say the same thing. See, u is a function of t comma b, right?
yes.
So the slope will also be a function of t comma b,
Yes, agreed.
right? So that is why this follows. So CV, CP, and all those things are state functions. We should remember that these are state functions. Okay. Now,
Okay.
for ideal gas, the simplification, the following simplification follows. Okay. For ideal gas, this happens. Essentially, what I mean is, I'll tell you what I mean. See, generally, you can write things like CV or dCV is equals to are you comfortable with this equation? Can you is it digestible?
dt is by dv. dv.
What have I essentially written? I have essentially written this thing. If I have there is a function of if z is a function of x comma y, then uh, then this thing follows. Okay. What have I written? I have written dz is equals to d. Actually, we don't write d. We write partial derivative. We need to respect partial derivativeness. Okay. We will have to write partials. Even here, even our definitions have to be accurate because total derivatives mean so a little bit of maths is there when I'm writing all these things. but essentially you understand that loosely speaking, they are the same thing, right? So this is there. Now, is this equation digestible?
Yes, this is
Graphically, what am I saying? Suppose your state is in as I like I'll draw the same state space diagram, state diagram or whatever, state space diagram, whatever. The same thing I've written. If you have any state function, right, and you move from one state to another state. So if I move from, let's say, here, here, and my two coordinates, two independent variables are x and y. So if I move from this direction, essentially because this is a path independent quantity, I could go using this route, right? And along this route, my y is equals to constant, dy is constant, and in this direction, dx is constant, right? And along these lines, the slope will be dz by dx and dz by dy. And these lengths will be dx, so dx and dy. Digestible, right?
okay.
Right? So I've written this thing. Basically, I'm kind of writing this. I'm doing this in a sophisticated manner, but essentially what I'm saying is that C the dependence on C, the dependence of specific volume on CV drops. So this thing drops. Right? See, if you remove this thing, this part, this will follow. That I can actually, because this thing holds, right? This is 0. So this thing goes. Right? And essentially then what this becomes? This becomes that CV is only a function of, okay, CV is only a function of T. Now, do you see why? It's actually here. This should also be partial. So if I keep my temperature constant, my CV value does not change with T. So sorry, if I keep my temperature constant, my CV value does not change with my specific volume. So it should be an independent quantity, right? So it should not be dependent on V or specific volume. So CV should only be a function of, which generally uh, is a function of T comma V for ideal gas. Okay. So this is important. This is something that you have to memorize. This is something that you will have to memorize. Memorize as in you need to know this a priori to even like, this is something that I actually at this point of time I don't want to show. I can show this, but I don't want to show this now. Okay. We will do the same thing to just quickly show you. Now, I'll just do the same thing. See, I can do the same procedure for you also. What am I saying is, in general, U is a function of E comma V for ideal gas. For ideal gas, uh, this thing follows. U stops, so the internal energy stops depending on specific volume. Can you tell me why? So for now, let's say that this follows. Okay. So essentially, then what will it be? It will be du will be. I know. Okay, this is something that I have missed. I have to write this first. So this thing follows. Okay. At a constant temperature, it just stops depending on the specific volume. So this will follow plus this is dt at constant v dt. Now, Jyotirmay ji, there is one term where I can make a substitution. Basically, in this equation, I can substitute CV somewhere. Can you tell me where?
In the portion du by dt with constant constant as volume, it's du by dt part.
This part, right?
Yes, yes.
And see, this thing I already told you that this is 0. This term will go. And so here, basically, we write CV is du by dt. Okay. See here, this is a total derivative. Even if for an ideal gas, even if you don't keep velocity, volume constant, specific volume constant, okay, even then, this du by c. I'll tell you what I'm trying to say. The diagram we drew, no. Suppose, okay, let me just write one more step. Then I'll write. I'll also substitute the CV value to. See, I'll write another thing for an ideal gas. CV was defined this way, right? Just note that here this operator is partial differential, okay? And this is a total differential. Now, what do I mean? This is important. So what do I mean is, suppose there was this state and there was another state, right? Right? And so what do I do is, this is, say, this is U1, T1, okay, dt. And this is U2, U2, T2. So, and one more thing, just as I mentioned to you, what we will do is we can also do this entire thing by doing this process. Once you keep temperature constant and then you keep specific volume constant, right? So here, this will be some U dash. Okay, this will be U dash. Okay, some U dash, but T will remain T1. Okay, that is what I'm trying to point out. And then from this, so let me also write V1 here. This will be V1. Okay. This will be V2 because we are changing volumes across this in this direction. And in this direction, we are primarily changing temperature. V2 will remain constant. Do you understand? Do you see this? Right? We could have gone directly to this. Are you able to understand?
Yes, yes, I can follow.
Okay. So now, if I ask you for this process, tell me what is du? So on this end, I'll just write you the I'll just write right hand side and left hand side for this path. Okay, for this path. So So between these two states, what do I mean is between these two states. So not for this path, basically between these two states. I'll remove this state, okay? For now, okay? So for this one, it will be U2 minus U1. This will be T2 minus T1. This will be, now tell me, this will be U2. So this will be U dash, okay? No. This will be U2
minus
U dash
U1. Okay.
will be T2 minus T1. This is important. Which implies what? Now from this equation, what does it imply? That U dash will be equal to U1. Right? So for an ideal gas, U does not change with V. That is what I wanted to say. See, U will not change with V. Along this line, because along this line, T was constant. Okay. So just first of all, in this equation, I wanted to show what is the difference between this exact differential or not exact total differential operator and this partial differential operator. Okay, one thing is that. Another thing is for ideal gases, internal energy is a function of only temperature because the dependence on specific volume goes away. It is not dependent on specific volume. That is how we are kind of defining ideal gases. Okay.
Yes. Okay. Dependent.
Another thing, huh?
Yes. Okay. Please go ahead.
Okay. So another thing which will follow is from this identity that H is also a function of only T. Can you tell me why? It is quite straightforward. H equals to U plus PV and PV we know is RT. Now for an ideal gas, U is only a function of T. So H will only which will be H will also be a function of only T. Okay, so for an ideal gas, both enthalpy and internal energy are only functions of temperature. In general, this is not always true. In general, U can be written as T comma V or equals to T comma P also. In that case, H will also be a function of T comma V, T comma P, or H is a function of what do you say? T comma V. And I'll give you a small example or small. Let's see if I can give you any example or not. Probably not at this point. Yeah, probably not at this point. Acha, you heard the quantity, heard the assumption of calorically perfect gas. Have you heard this term? There's
Well,
an
I've
ideal
heard.
gas and then there's a calorically perfect gas.
I'm sorry, I cannot recall, but I have heard it.
You've heard about it, right? So
Yes.
calorically perfect gas is a subset of ideal gas where CV is largely not a function, is a constant. See, when you remember in our early high school days, we used to say CV equals to 3 by R, 3 by 2R. CP was 5 by 2R. And this was for monoatomic gases. You remember? For
Yes.
diatomic
Yes.
gases, it was 5 by 2R and 7 by 2R. You remember?
Yes. Yes.
These were, these were, these were, I'll write this thing for calorically perfect gas models. Cp is 5/2 or some constant. Okay. Acha, I have now important thing is I have mentioned models because as we discuss now we are saying that Cv is generally a function of T. Then what is this class of gases for which Cv will be constant? Cv cannot be constant because temperature will vary. How can Cv be constant? So we should note that this is a model. We are kind of modeling the gas. If we assume the Cp to be constant, then this becomes a model, right? This is a modeling thing. You are modeling it to be Cp to be roughly constant. You understand?
Okay. Yes.
You understand?
Yes. Yes.
And similarly, see, even ideal gas is a model. See, no gas is an ideal gas, to be honest. Okay. See, ideal gas, what do you mean? When will you get perfectly ideal gas? When in the limit T tends to 0 and T tends to infinity. But do you have any gas at 0 pressure and infinite temperature? No gas. Any gas will behave will be almost ideal, but it will have small deviations. So even ideal gas is a model. Okay, so CV has a strong say. See, CV is generally let's say uh, let me in this equation. Okay, just to show you, just to tell you what do I mean by model and all that. Say this thing normalized by what do you say? How can we normalize this? Can we normalize this? We can normalize this by saying that into V star or V ref by CV ref. Okay. Suppose this quantity is let's say 1. Okay. And then I am having another quantity which is dCV by dt at constant T at constant specific volume and T ref. Okay. And this is 10,000. Okay. Now, what do I mean? If I kind of write this equation in terms of this thing, so basically what I have is dCV by dt becomes will become direct. Okay, and then this will become 10,000 divided by T ref. Okay, and this will become 1 by V by V ref. Do you see what I have done? Digestible? I just said I've given it two numbers. That's it. Let's say these are two numbers. This one is a large slope. See basically we are saying there are slopes, right? CV will depend on T and V. So if CV is sharply depending on temperature and not so much depending on volume, then roughly we can say this. Let's say, right? If I take these numbers, you understand this, right?
Okay.
Okay, and now under the condition, suppose under this condition, Under this condition, what do you think is important? Say is 1, or let's say 10, or let's say dx, or some length ds. Okay, then what it becomes? This becomes, is it okay?
1 ds.
Oh, this, let's not use s. Let's not use s, so that you might get confused with entropy here. Let's call it L.
dl.
Or
Okay.
okay, so some length. Okay. Now is this okay?
1 dl. Okay.
And can I not say this?
Okay.
1001
Roughly
is roughly equal to 1000, right?
same
Let
order.
me not
Okay.
let me not use this. Let me use this at this point.
Approximate. Okay.
Right? What am I kind of saying? I am kind of saying this thing. Basically, I've removed the dependence of this one here, right? You understand?
Okay.
No, do you understand, or is there in
Yes.
like
No. I'm following it. I can follow. I can understand.
so what I'm trying to imply here is that when suppose your changes in temperature and volume are kind of comparable, but your slopes are strikingly very different. One is like, let's say 1000, other is 1 in normalized terms. Then you know that the weak dependence can be neglected, and only in that cases we can say that Cv is a function of only temperature, or U is a function of only temperature, and that happens for an ideal gas, or that happens in the limit P is a very low quantity, T is a very high quantity, right? They will be exactly zero only in the limit P tends to 0, T tends to infinity, when that limit is reached, but they will have some value, right? Even an ideal gas is a real like in practical it will have some deviation. So that is what I wanted to just say here, that that is also a model in itself. That is what I wanted to try, wanted to imply. Okay, did you get the idea?
Okay. Means it is, yeah.
And what other thing was I going to discuss? Just let me see. Yeah, so for ideal gases, I actually discussed this part even in the last class. This was done by Jules. Okay, this was done by Jules. What he had done was he had taken a temperature bath. He had taken a cold bath, a water bath, and in a cold bath, what he had done was he had connected two vessels. One was pressurized and one was evacuated. And what he had done was, so this was he what he had done was what he had done was he had had a two pressure vessels. One was pressurized, other was evacuated, and then he opened the wall so that the gas filled both vessels. And he noticed that and this was an ideal gas. It was a gas which had like very high temperature, relatively high temperature, and very small, very low pressure. The pressure was not very high. Okay. What he noticed was that there was no temperature change that happened during this process when he opened the wall and the wall expanded. And because this was a free expansion, there was no work done, right? There was no boundary work, right? So
Yes.
delta W was zero in this case. He also noticed that uh, he also noticed that the water bath, so basically he measured the temperature change in the water bath. Okay, tea water. He noticed that that had also not changed. From which he implied that this there is no heat exchange that has taken place. So delta Q was also zero. Okay, and then he noticed another thing. So these two things implied that du was zero. Okay, internal energy had not changed, but clearly earlier it had some pressure and volume, right? P initial and P V initial. But P final and V finals were not equal to the initial value. So P final was let's say half of. Uh, so at least we know that V final was 2V initial, okay, and P initial was equals to. So basically P final was P initial by half. Okay, this is so. From this observation, he noticed the velocity had changed. Sorry, velocity I'm saying specific volume had changed, pressure had changed, but internal energy had not changed. And he also noticed the temperature had also not changed. So from there, he concluded this was an empirical observation, okay, that U was a function of T. Important part was that he had done this for an ideal gas, okay, and only for an ideal gas, U is a function of T. So this was called as Joule's experiment. Okay, I think most of it is done. First question, I took too much time in discussing this thing. Okay, anyways, let's discuss the second and third questions for time being. What is it? So now you understand this part, right? Generally, this will you understand this part, right? Now,
Yes, yes,
okay.
it's clear now. Ideal gas only.
An ideal gas undergoes a constant entropy process in a closed system. The heat transfer and work are respectively. Okay, so we need to find out. So it's a constant entropy process. Have you the video lectures have not done entropy, right? Yet
No, we haven't reached there yet.
entropy is done, is it, in video lectures?
Entropy, I mean the entropy part. No, means I haven't covered it yet.
Okay. Anyways, so in an isentropic process, Ts is zero, and
Yes.
it's a closed system, so there is no mass exchange. So the m is a constant. What else? Uh, um, ideal gas. Okay, that's okay. So the heat transfer and work are respectively. It's an isentropic process, closed system. I think we need to know we need to say that whether the process is reversible or not.
Yes, yes. That is what I was thinking. It is not mentioned anywhere. It's reversible.
I think it should be reversible. Only then we can make some progress. Let's say, let's say it's a reversible process. In that case, del Q will be TDS, which will be equal to 0. And then del W will be du, which will be equal to what? Now tell me. We have just done this. What is du equals to for an ideal gas?
Oh, we CVDT that we did.
Yes, CVDT. Okay, so I think, yeah. So that is this one was a simple thing. Let's look at the next one. Which of the following property remains same for a steady flow process? Are you aware of what a steady flow process is?
Yes, I'm aware. So it should be the volumetric flow rate, or maybe not steady flow process, or the mass flow rate should be constant.
Yeah. Why?
Because in case of the volume, it is a function of the density, which can vary with respect to temperature. But the steady flow process, in a steady flow process, there is no concentration of mass in the system.
Right. Essentially, what you're saying is dm by dt is 0,
Yes.
which is also equal to summation m dot m. Which we can write as it's actually the correct statement to say is that summation m dot in is equals to summation m dot out. Okay, so the total mass inflow is equals to total mass outflow. Okay, and that is what remains constant in time. They have also not mentioned remain the same, they say, but they should be constant in time. But largely mass flow rate is the correct answer. Okay, the construction of this question is not very precise. Anyways, now let's do this question. What is it? Which of the following option does not represent a steady flow process? Sir, I think, okay, I don't mind. Can you tell me which one is not a steady flow process?
I mean, pump is a steady flow process. Compressor is also a steady flow process. In nozzle, I mean, the mass in is mass out. The velocity can change depending upon area. So the pressure cooker maybe is not a steady flow device.
Yeah, it's a pressure cooker. Why? Because pressure cooker, there is no mass inflow. There is only a mass outflow. Okay. And so because there is no mass inflow, let's see that this is right, because that summation m dot n is 0. So dm by dt cannot be can only be 0 in case there is no mass outflow also. So when there is no mass outflow from a pressure cooker, only in that case dm by dt will be 0, which means that the system is not, there is no process happening. System is at some state, is at some state. It's not moving. So there is no process that is happening. But if there is a steady flow, then these two should be equal, and which implies that these should be non-zero finite quantities. Okay, but in a pressure cooker, these one of them is 0. Okay. Anyways, what else? Next question is. Try to solve this one on your own. Let's see.
The following option is correct.
Do you know what flow work is?
Flow work is basically the integration of VdP that we.
No, that's not the flow work. So flow work is essentially when you have, it's actually comes up in the definition of enthalpy. It's actually H equals to U plus PV. So PV is the flow work, okay? PV is the flow work. Okay. This is basically, we can call it, it is essentially a kind of a work, but remember that this flow work is actually a state function. PV is a state function, right?
Okay, yes.
So that is why it's a little contradictory when you say flow work is a state function, but that is why I don't want to call it flow work or anything. But anyways, you tell me you know what this question means. Okay, so go ahead and try to solve this. Any boundary moving in a pipe? Is there a boundary work?
Uh, well, there is no energy going in and out, so I think boundary work should be zero over here.
No,
And
but why boundary work? Energy will be involved in like when you discuss boundary work. Why energy comes into the picture? It won't.
okay, because there is no movement of boundary. Yes, it's not a
Yeah,
piston assembly,
yeah.
so boundary work should be zero because there is no displacement work.
So one important
And
thing is we know that only these two options will follow then.
hmm,
But is there any flow work?
I mean, flow work is in wasn't necessarily
The answer is flow work will be non-zero.
yes.
And roughly you can know why, because as I mentioned, flow work is PV. In a pipe, there will be a finite pressure, there will be a finite density, which implies there should be a finite flow work.
Yes, it should be a finite flow work.
Okay.
Yeah, flow work should not be zero. Yes.
Uh, a small homework or something, you can go and look up why PV equals to flow work, or what is flow work, okay, and why it is equals to PV.
Sure.
Okay,
Yes.
fine. So then let's look at another question.
Diabatic nozzle. Diabatic nozzle. Q equal to zero.
Happens in a nozzle? What? How do you define nozzle?
Nozzle. Well, there is an inlet section and an outlet section, whereby the outlet area in this case it is less than the inlet area.
No, that's not the correct definition of a nozzle. Interestingly, you're right.
Then
You're right for a specific case, but in general, that's not true.
then what should we say? Like so diabatic, kinetic energy increases
Okay,
because
in your specific case, in whatever case you are imagining, and I'm also well aware of that case. What happens when the inlet area is larger and outlet area is smaller? What will happen?
there is the acceleration of flow will take place.
Okay,
Means
which
the
acceleration
velocity
of flow will do what?
means
Let's say in terms of kinetic energy.
yes, the outlet velocity will increase because for the same rho 1 a1 v1. So this time the I am assuming density is constant. So acha, but the air is accelerated. Okay, so
Yeah.
means the v2 should be greater than v1 outlet velocity.
Yeah. So
That means the
one important thing is that it's not the so inlet area is not the criteria of defining a nozzle. Okay, that is one important. Uh, I'll tell you why. In supersonic flows, no, when flows are supersonic, the inlet area will be smaller than the outlet area, and the flow will still accelerate.
okay, yes, yes.
Is this counterintuitive, or you're able to adjust that?
Well, generally in the bell shaped designs of the outlet, uh,
Yeah,
we in the
yeah,
supersonic
converging,
heating, yes,
diverging nozzles. Yes,
yes,
yes.
yes. Okay, yes, sir, it's okay. So,
But
but in this case,
so
but in this
generally
case,
we'll say kinetic energy increases. Okay, that is the definition of nozzles. Okay.
okay, okay. But over here, the kinetic energy will increase, and the
Now about the temperature. It's an adiabatic nozzle. Okay.
right.
So
So
here
the
we will
external,
not apply the first law. Okay, we'll have to apply. Actually, we are going to apply first law only, but
yes,
we'll have to apply it in terms of not in terms of internal energy. We have to apply it in terms of kinetic energy. Okay. So D will be du. plus D kinetic energy plus D potential energy. Isn't it? What is this? This is mechanical energy, okay? This is
Yes.
mechanical energy and this is thermal energy. Total energy is mechanical energy plus thermal energy or internal energy. Okay. So whenever we were writing du equals to del Q plus del W, we were essentially writing thermal energy equation, assuming that the mechanical energy is zero. But a nozzle, mechanical energy is not zero because there is a thermal to mechanical energy transfer that is happening. So in nozzles, generally we will have the nozzle at the same height relative to the ground. So change in potential energy goes to zero. Okay. Now because kinetic energy is increasing, thermal energy or internal energy will decrease. Okay. But that does not imply that the temperature will decrease. This question is incorrect. Temperature, we cannot say anything about temperature. Just like how we cannot say anything about the inlet and outlet area, we cannot say about temperature also. I think in supersonic nozzles, temperature decreases or something. I don't, temperature increases or something or what? Let me think. Let me think. When you will have drop in energy, CV is also always a function of temperature or what? But generally it will be also a function of pressure. So pressure drops. Okay. So this is something that I have to think about. So U is a function of temperature and pressure, right? A function of temperature and pressure. Generally across a nozzle, pressure drops also. Okay. Let's look at the definition of nozzle, just to be clear. One more thing is that it's an adiabatic nozzle. Okay. So,
So the del
now
Q across
du,
the U is 0.
again, you're not supplying any energy to the system. It's an adiabatic system. So this DE will be 0. Okay. Actually, no, DE will not be 0. No, sorry. DE will be delta Q plus delta W. Okay. In a nozzle, work done is 0 or what? Work done is also 0, I feel. Right. Both of these terms will be 0 because adiabatic and you don't have any boundary work also. Let me see. I am also a little confused now. Let's quickly see this. Yeah. Our nozzle is defined. Nozzle is defined which increases the velocity of the fluid at an expense of pressure. So pressure has to drop. Okay. So pressure drops, but velocity increases. Okay. And there will be no work also. You are not supplying any work to the system or anything, right? So this will generally be 0. Okay. So now pressure drops. So what should happen with temperature? Pressure. Now the important part is do we have a qualitative understanding of if pressure increases, does our internal energy increase or decrease? Or if our temperature increases, does our internal energy increase or decrease? For one thing is that this is always true. CV is a positive number, right?
Yes.
Positive number. So we generally know that with increasing internal energy, temperature also increases. But with pressure, I'm not sure. What happens with pressure? Sure. I'm not sure. Let me check. Is it increasing or decreasing? It's positive or negative, that I don't know. Let me check. It should be able. It's good. Or let me ask ChatGPT only.
Yes.
Right. So
Channel flow.
okay. So loosely speaking, without being too specific, we can say the temperature drops. Okay. Although it is not very precise, but we can say that this temperature will drop. Okay, temperature decreases.
Okay, because it is a subsonic flow. That's why. Okay.
No, it's not about subsonic flow, but even because the main reason is that okay, the main reason is that either it is subsonic or supersonic, the temperature always drops in a nozzle flow. And in a nozzle flow, generally you will have a very large area. What do you say? Area change in area. So that causes what do you say? That causes the acceleration, the flow. It's a little complicated because you will require a little of gas dynamics to look what happens in subsonic and supersonic things. But generally speaking, see, if you consider the case of friction, if there is friction in the nozzle, then there is a possibility of having a temperature rise, but that happens only when your area is constant. But in a nozzle, area remains, area increases or decrease or changes, area changes. So in both these cases, in a nozzle, temperature drops largely. Let me see if we have a thermodynamic explanation for that. Does the temperature always drop? Hmm, hmm. At least, okay, for an ideal gas, this is always true. See, this says no air, no? That is important. I forgot this part.
Okay,
It's
that means
air,
it is
right?
the
For an
that
ideal
means
gas,
the
U is only, this is zero for an ideal gas, right?
yes.
This thing I missed. For ideal gas, this is zero, right? So then temperature drops. This is indeed this is precise. I made a mistake saying that this is not precise. This is a precise question. Nothing wrong with it. Anyways, let's move to other questions. Okay, let's do this one. This is a interesting one. It feels. What is it? So consider an evacuated rigid bottle of volume V that is surrounded by the atmosphere at pressure T naught and temperature T naught. A valve at the neck of the bottle is now opened and the atmospheric air is allowed to flow into the bottle, the air trapped in the bottle eventually reaches thermal equilibrium with the atmosphere as a result of the transfer of the bottle. The valve remain open during the process, so the trapped air also reaches mechanical equilibrium with the atmosphere. Determine the net heat transfer through the wall of the bottle during this filling process in terms of properties of the system and surrounding atmosphere, and mention the direction of transfer of heat. Okay.
Yes. So
Okay. So initially pressure is zero.
yes, it is evacuated. Yes.
Right.
Right.
So initial state, everything was zero because there was no mass or anything. What is the final state? Final state is P naught and T naught, right? If I apply the internal energy, this thing, thermal energy equation, I will say delta U equals to delta Q plus del W. Again, my signs of Q and W are maybe a little different with yours, but does not really matter. It's air, right? It's air, it's atmosphere. So this will be volume is given. Then you should know rho naught. Rho naught will rho final. Rho final. So this becomes mass. Then you write CV and dt. And dt will be what? T naught minus zero. Why am I saying zero? Because there was no mass initially. So instead of saying delta U, we should say U final only because U initial was zero. You understand? So we
You.
can say U initial is zero only now.
Okay.
Because there was no mass inside the vessel.
Yes, there was no mass. It's evacuated. So okay. U initial is 0.
So this is my U final. And I can go ahead and write what is my rho F also is. What is my rho F? RT naught by P naught. Is that okay? Again, another important thing is I know that this is a free expansion process. There is no work done in this process, right?
Right. Yes.
Free expansion. So I can actually put this delta and all I can remove. I can put just Q and W. So W is zero. So Q will be this much. One thing. So Q should be equal to cos. Uh, Wait, let me think. Hmm. Okay, no, wait. I cannot wait. There's a mistake which I have done. Oh, I've done a mistake. This is not a constant. This is not uh, a closed system. I cannot use this,
Oh yes. Yes.
right? I have also have to add this thing.
MH.
Actually, I can just say and right. Is this okay? Basically,
Yes,
what am I
I'm
invoking
listening.
here? So this is what it is. Should be mass. Okay, M. They're using small m. I'll also use small m. Okay. So then what is the mass of the system? As I told you, rho f into v. Right? This is the mass which entered the system, right? No, wait. So this is UF. So then I actually write that UF equals to Q plus this is mass into HN. Now what is HN? HN is CP T naught. That's okay, right? So then Q becomes the UF minus this quantity, which is what? Which is equals to minus R, which is basically this. Okay.
Okay. So that's okay. So,
Now another important thing is the ideal gas equation that we have not used yet. Okay. What is the ideal gas equation? P naught equals to R T naught. Do you agree with this? Why why will V come here where V is the volume of the bottle? Because finally the gas inside the rigid tank, which is in the final state, it is occupying that volume. The pressure is known to us as P naught and temperature is known to us as T naught. So we know that T naught V is equals to RT naught.
okay. Okay, but
Right?
right, but as per the question, initially it was evacuated, right? So
Yeah,
then
I'm using the final conditions to
okay,
write
final
this.
condition.
Finally, it is it says final also P naught and T naught conditions are prevalent, right? P final. Let
Okay.
me write this. Isn't it? Atmosphere pressure is not going to change, right?
No, it's
And its temperature is also not going to change because it is a large capacitance system, isn't it?
yes. So T0. Okay, it's clear now.
Right?
It's equal
Or
to
maybe I
T0.
can write this just for the sake of that is okay, right? And then we can substitute that PF, this all those things. So then basically I can write RT naught as PF T naught into V. V square, I think. This will become what? Issue is there, man. Some dimension issue is there, it seems. P naught into V. Oh yeah, the issue is P equals to rho by RT. No, P equals to rho RT, right? Rho RT.
So PVMRT or P rho RT. P equals rho RT.
So this should be P naught by R by RT naught, right? Not RT naught by P naught. This was rho F, right? You remember?
So, okay, yeah. Just,
Let me write this.
it was rho V CVT naught.
What is this? This is mass. Mass M final.
Yes.
This is okay. No? Things up. Okay, and this will also be P naught by P naught by RT naught. Okay. That is important. And then P naught by RT naught. So now, okay, wait. So will be some the issue was of units. I made a units issue. So this RT naught gets cancelled. So you get what? Q equals to minus T naught V. Now this is okay. What does this mean? That the system requires to will release some energy to the surrounding. It will lose some energy surrounding. There will be an heat exchange to the surrounding.
Okay, minus P. Okay. Means the direction of the transfer of heat. Okay. So the system will lose heat to the surroundings. Okay. Minus P naught V.
Okay.
Okay.
Let me just quickly think, what does this imply? When you so if you notice, this is the flow work. Okay, this is in some sense. Okay, one thing is that, let me think, what does this mean? Okay, I think I don't have any example coming to my mind where we notice this to happen. Yeah, I think this is okay.
Yeah.
Yeah. So I'll close at this point. I think 2 hours, we've gone 2 hours. I'll stop now. If you have any questions or anything, we can discuss. Otherwise, we can close.
Yeah, it's okay from my side. Thank you for being patient.
Okay. Thank you so much.
Okay.
Yeah.
Thank you.
Okay. Let's meet next. Yeah.
Sure. Until then, see you again.
Yeah. Great.